So in the previous sessions of firefighting, we have completed hydraulic calculation using manual method, water demand calculation, correct, pump settings, and correct. Now we have to discuss uh, carbon dioxide and FM200 systems. So to extinguish the fire, okay, small fires and all, we can use fire extinguishers. Then we can use water, but everywhere water is not permissible, right? For example, in the fire classification in the starting classes, fire extinguisher selection classes, we have discussed we are having class A fire, then class B, class C, class D, class K, as per Nfpa 10. Class A means like combustible solids only. Class B means combustible liquids, petrol, diesel, all the chemicals, paint. Class C is energized electrical equipment. Especially in class B, you can't use water, right? Because if you are using water, the density of water is higher than the petrol, diesel and all. Or that's why like a less denser fuel will be rising upside, water will be flowing down. It will be difficult to extinguish the fire. So the extinguisher can't create a layer above the fire surface. That's why class B fire, you can't use water always. Class C also. Class D is combustible metal and class K is, we are using wet chemical type. Class D special purpose dry powder we have to use, combustible metal. Class C is energized electrical equipment only. There also you can't use water. Liquid type extinguishers, you can't use class C. You can't use, no, class C, you can't use liquid type of fire extinguishers because that may cause energized electrical equipment, no? Short circuits make it. Correct. That's why there we can use gases. Means gases, either we can use carbon dioxide like Nfpa 12, National Fire Protection Association 12 we can use. Nfpa 12 carbon dioxide fire extinguishing system. This standard we can use. Okay. Nfpa 12, or we can go for Nfpa 2001. Nfpa 2001 is inert gas systems. Nfpa 2001 is inert gas systems. Foam is also there, but foam we can't use in class C. Foam in the fuel cases only we are using. So which one we have to use? Nfpa 12 is carbon dioxide. Nfpa 2001, we are having clean agents. Clean agents, normally we will be having inert gases and we'll be having hollow carbons. No, hollow carbon component means inert gas with a combination of fluorine, chlorine, any hollow carbon content will come. Okay. Carbon dioxide, where we have to use, see, in class C fire, energized electrical equipments, normally we will be using this. Most commonly, especially in generator room, then electric means computer laboratories, server room, data centers, UPS room. There we can use this gases to extinguish it. But how the gases is extinguishing the fire, the type may vary. For example, carbon dioxide will be doing the smothering only. Smothering means suffocating. Carbon dioxide will be fully filling within the space. Accordingly, the oxygen concentration will decrease. If there is no oxygen, no fire. Correct. That's the way the carbon dioxide is working. Advantage is whether there is carbon dioxide or Nfpa 2001 clean agent, the advantage is there is no residues remaining. Once the fire has extinguished, once the fire has completely extinguished, no, suppose if you are using dry powder, after the extinguishing, there will be dry powder residues will. Correct. After extinguishing using water, the file might get damaged. No? So the residues will come. But in gases, when you are using, no residues will be coming after the extinguishing of fire. So that's why carbon dioxide smothering is the way it is doing. Means it will be creating a layer. So it fully filling within the spaces. Accordingly, the oxygen concentration we can decrease, then fire as well. Okay. Nfpa 2001, we are having clean agent. Clean agent is hollow carbon and inert gases. Inert gases means argon, krypton, helium, that one you can use. Hollow carbon means we are having different types. The most common type that we are using is FM200. Factory, mutual, 200 type, HFC, 227 EA, that's a code name of FM200. Okay. This is also gases only, but the way of doing the extinguishing method is different comparing to the carbon dioxide. Clean agent system, carbon dioxide, wherever the people are there, it is not possible because occupied region, once the carbon dioxide has fully filled, the oxygen concentration will be decreasing. So occupied spaces, it will be difficult to use this fire extinguishing system. But if the people are working within the server rooms and all, you can go for clean agents because it is not harmful for the human. Rather, inert gases will be removing the chain reaction. Means if the fire has to be happened, the fuel has reached the flash point, right? That's why we have to heat it up. So when you are using the clean agent as an extinguishing system, all these clean agent gases will be entering into the spaces. It will be absorbing the heat from the spaces or from the fuel. So the fuel will be going below the flash point. Accordingly, the fire we can extinguish. The chain reaction, it will be cancelling. In fire triangle and fire tetrahedron, we have studied the concept. So it will be removing the chain reaction or the heat to reach the flash point. Accordingly, only the clean agent. So even the clean agent is slightly, because carbon dioxide is abundant in atmosphere, so that is cheaper comparing to the clean agent. Clean agent is slightly more price comparing to carbon dioxide. Okay, that's why occupied region we can go for this FM200 spaces. Unoccupied region we can use for this carbon dioxide selection. We can study carbon dioxide first, then we can move to FM200. Okay. Normally, normal MEP contract is whatever the services in fire services it may, you're working. Normal MEP contract is not having the authority to do the firefighting task. Civil defense approved contractors only can do, but the company that you are going to work is a firefighting company or an MEP company is already having the permission of civil defense, then they can do it. Especially this carbon dioxide system, FM200 system, everything has to be done by the specialist subcontractors only. They might be having their own softwares. So that's why nozzle selection, pipe sizing, everything separately. They will be having their own handbook to do it. But necessary things you should know how to calculate. So we will be calculating how much quantity of carbon dioxide or FM200 is required to extinguish the fire. Correct. How the system is working, for example, if I am having a space, say a server room. Okay. And we will be using cylinders outside, carbon dioxide. Cylinders we can use. Then, 1 second. Yes. Okay. And all these cylinders will be connecting together. Then it will be going inside. There will be using spray nozzles. Okay. The same time, inside the spaces we will be having detectors. All these detectors will be connected to the control panel only. So in case of fire or smoke, the detectors will be identifying it and the signal will be going to the control panel. The control panel here, above the gas, we will be having a automatic valve opening system, like a solenoid switch. So the control panel will be sending signal to this automatic valve. This will be automatically releasing the gases. It will open automatic and it will be releasing the gases. So carbon dioxide will be spreading inside. Accordingly, the fire we can extinguish. That's the way it is working. Carbon dioxide extinguishing system. Very limited component we will be having inside. Correct. This one. Sometimes one cylinder, sometimes multiple cylinders we require. Okay. Anyhow, how much quantity of gas we required within it that we have to calculate. Okay. Carbon dioxide, when we are using, we'll be using a method called a total flood method. Total flood method means total flood method is there. Direct application method is there. Direct application method means you can see the fire extinguishing system that we are using. Fire extinguishing system, no fire extinguisher, it is kind of direct application only. Exactly, directly the carbon dioxide will be guiding on the surface of the fuel or the fire happened. That is called direct method, but we are dealing with the total flood method only. Means the the carbon dioxide will be flooding inside, total flood method. There is also total flood method we will be using for two types of fire. The first type of fire is called surface fire. The second is called deep-seated fire. deep-seated fire. So where we are using surface fire, the normal server room, suppose if you are having a cable, on the surface of cable it is burning, correct. Suddenly we can extinguish it, that is called a surface fire. The fire, it has happened due to the surface and the fuel is on the surface only most of the time. Deep-seated fire means the fuel intensity is too high. For example, battery, UPS, battery room and all, UPS rooms. There, the fuel deposit, no, for example, I will show that what is this deep-seated fire. For example, a waste storage area. These kind of fires are called deep-seated, correct? If you want to extinguish the fire and all, see, the fuel will be like large fuel and it is very difficult to go inside. It is called a deep-seated fire. It is very difficult to extinguish it. It's called a deep-seated. And surface fire. So the design deep-seated we will be considering normally within the UPS rooms and all. Okay. Rest everywhere we are using surface fire only. Both the thing we can discuss first. Okay. Carbon dioxide, first one, surface fire. For example, normally in server room we can use it, or any fuel area you can use this one. For example, minimum concentration of design concentration of carbon dioxide is there. Minimum design concentration of, in no case, shall a concentration less than 34% to be used. That's why minimum design concentration, there is a term, has to be used to 34%. That's why if you are designing a server room, a data center room, 34% concentration you can use and you can design accordingly. But for time being, I'll be having a space of, when we are calculating the space, let's say, example, I'm having a room. The width of room is like 10 feet. Okay. This side will be 15 feet. Height will be 11 feet. 11 feet. Okay. Please make sure your mic. Okay. So you have to calculate the volume. Even if you are having false ceiling within the space, if you are having a false ceiling within the space, when you are calculating the volume from the bottom of, from the finished floor level to bottom of slab, the entire height has to be considered. Okay. And the type of fuel that you are storing inside, or the type of fire or combustible that you are storing inside. Let's say different types of combustible we will be having. Acetylene. Here you can see this. All this data I have taken from Nfpa 12 only. Table number 5.3.2.2. Minimum carbon dioxide concentration for extinguishment. We are storing acetylene, acetone, butane, carbon disulfate, gasoline. Gasoline means petrol region and all the petroleum products you can consider under the gasoline. Gasoline, the minimum concentration you can see. Minimum design concentration, how much it is? 34%. Server room, if you are using carbon dioxide, server room nowadays we are using FM200 only, but you can use the same 34% for server room. But let's say I'm using like benzol. Okay. Benzol I am using. Here you can see benzol or benzene. I'm storing benzol inside. What exactly you are going to store that will vary, right? I'm storing benzol. I have taken that as benzol. In the top side, you can see I'm storing benzol. And what is the length, width, and height of my space? Because I need to calculate the volume. Okay. Length is 15. Length is 15. Width is 10 feet. Height is 11 feet. Height is 11 feet. Okay. So the volume will be, as you know, length into width. You will be getting area. Area into height, you will be getting volume. 1650 feet cube squares. Correct. That's the volume of my space. Carbon dioxide quantity, when we are calculating, few considerations we have to do. The first one, we have to calculate the basic quantity, minimum quantity that we required inside it. Along with that, we have to consider a material conversion factor. And if there is any unclosable opening is there, through that opening, air will be entering inside. At the same time, when the air is entering, carbon dioxide will be displaced. This quantity has to be considered. That is called unclosable opening. And next one, if you're having unstoppable ventilation within the space, if you're having a ventilation, but normally ventilation will be stopped in case of fire, but unstoppable ventilation is there means how much quantity of fresh air that you are introducing or how much quantity of air you are exhausting. The same makeup quantity of carbon dioxide has to be introduced inside. That is called unstoppable ventilation. And by considering the temperature within the space, that allowance also has to be considered. All these things one by one we have to add. Then finally the quantity we can calculate. Okay, one by one we can see the first one. Basic quantity of carbon dioxide. Basic quantity of carbon dioxide we can do by two methods. Okay, the first method, volume of space divided by volume factor. Basic quantity, volume of space divided by volume factor. Volume of space we have already calculated 1650 feet cube. Volume factor you have to take from Nfpa 12. Means this is like each feet cube of space, how much pound of carbon dioxide can come. That's a value that you can take from this table. Volume factor, table number 5.3.3.8, volume factor. Volume factor is there. Flooding factor is also there. Both you can use. Okay. Anyhow, what about our volume of space? Our volume is 1650 feet cube. 1650 feet cube. 1650 feet cube. Okay. So volume of space in feet cube up to 140. This one. Our case is 1650. So 1650 will come in this range. Correct. In this range only. Okay. In our area was 15 feet length, 10 feet, then H1. Okay. So how much it is? In this case, the volume factor will be getting 18. 18 feet cube per pound. Okay. So that way you can calculate it. 18 feet cube. This one I have taken here. Correct. Volume factor is 18. Now the basic quantity volume of space will be how much? 1650 volume of space divided by volume factor 18. So we required 91.66, let's say 92 pound. Like that you can find. Okay. Or another way, volume of space multiplied by flooding factor. This is divided by, multiplied by flooding factor. Flooding factor you can find from here. 0.056, that is a flooding factor. Unit you can check. This one is a kind of specific volume and this is a kind of density. Not exactly that one, but unit you can check. This one is like a pound per feet cube, or another way, kilogram per meter cube. This is density only. This is meter cube per kilogram or feet cube per pound. Correct. So this one is like a specific volume. This one is like a density. Means each kilogram or each feet cube of space, how much kilogram of substance we required. That's called a flooding factor. This one, each kilogram of carbon dioxide can occupy how much feet cube. That is called the volume factor. So if you are selecting volume factor, the space in volume, feet cube divided by volume factor, or flooding factor, we know that is 0.056. For the same volume, flooding factor, we are getting 0.056. Okay. So 0.056 into 1650. So 1650 into 0.056, how much you will be getting? 92. Slight variations will come, but say. Correct. So either you can divide this value or you can multiply with the flooding. Both the equation is correct only. So basic quantity of carbon dioxide is volume of space divided by volume factor or volume of space multiplied by flooding factor. Okay, this one you can follow. So we have calculated 92 pounds of carbon dioxide we need. 92 pound. 1 kilogram is 2.2 pound only. So we are calculating in pound. Later we can convert into kilogram. The next one, material conversion. Up to 34% density, you don't want to consider this material conversion. It is not mandatory. But if you are considering the material or the design concentration of carbon dioxide requirement is higher than 34. Here we got benzol, the minimum design carbon dioxide concentration, 37% only. What 37% means? If the oxygen concentration within the space is going less than 16%. Normally in the atmosphere, we are having 21% of oxygen. Within a space, also we might be having 21% of oxygen. If the oxygen concentration within the space is going less than 16%, then up to a certain extent, we can extinguish it. So it doesn't mean that when the carbon dioxide is entering into the space, it will be completely removing the oxygen. Oxygen concentration, it will be drastically decreasing accordingly. Okay, anyhow, 37% of concentration we need within the carbon dioxide concentration we need within the benzol, for benzol within the spaces. Okay, so up to 34%, this value is not mandatory. You don't want to consider any material conversion, but above 34% you should. Now we are having 37%. Okay, so 37% definitely you should consider, means this value has to be multiplied with the material conversion factor. Okay, so that's the second quantity. The first quantity we got Q1. Q1 is the basic quantity of carbon dioxide, we got 92. And along with that, considering material conversion, basic quantity into material conversion we have to find. Material conversion we can find from this table, this chart. In this chart, you can find x-axis we are having minimum design carbon dioxide concentration in percentage and conversion factor here as well. Conversion factor. And your minimum concentration up to 34, that is fine because the conversion factor is 1 only. But we are having 37%, right? So this is 34, correct, 35, no, 34, 36, 38, 40. 37% will come somewhere here. This is 1, 1.25, 1.5, so 1.2, 1.4, 1.6, 1.8, 2, like that it will come. That is between 1.2 and 1.1 in our case, right? This is a curve. Within this curve where we are getting the coinciding point for 37%. 37%, the conversion factor is, you can consider 1.1. If it was 50%, then the conversion factor you will be getting 1.6. Correct, like that you can find. Anyway, in our case, we need the material concentration factor since it is higher than 37. If this was 34, this will be 1 only. You can neglect it. But our case is 37. So material conversion factor is 1.1. Okay. Now you know the basic quantity Q1, 92. Now Q2 will be 92 into 1.1. Means basic quantity into material conversion factor, you will be getting 101.2, let's say 102 pound will be counting. Okay, so along with the basic quantity, we have added material conversion factor. The next two is conditional only. Unclosable opening. Unclosable opening means within the space you're having an opening. That opening is not possible to close. Anyhow, if the space is air conditioned, normally opening will not come there. For example, this area of opening, it is like a 2 meter by 2 meter or 2 meter by 1 meter. The area will be 2 meter square. Okay, 2 meter square. And we should consider the height. Okay, there is a term called height. This height H2, that height is conditional only. When you are considering the height, because from the middle of this opening to the top side, how much height you are having, this one you have to select. Based on this height, you have to select a value. Okay, anyhow, if you are having unclosable opening, through this opening, a little amount of carbon dioxide will be going outside when you are spraying it. At the same time, the air will be entering inside as well. Okay, that's why carbon dioxide loss due to the opening, you will be having an allowance. That allowance has to be added along with this 102 pound. How much allowance can come? Carbon dioxide loss due to the opening is A1. A1 means area of this opening. 2 into 1, that is 2 meter square. You have to convert that into square feet. Okay. Area into QL, leakage rate. There is a term called leakage rate. This leakage rate has to be taken from the graph only. How much it is? Anyhow, let me select this one is like 4 feet. Okay. This is 4 feet and this is 1 feet. Okay. And from the middle of this one to the top side, I'll be having 4 feet. Middle of this one to the bottom of ceiling. How much? I'm having 4 feet. Okay. This is called H2. H1 we have already taken the building space volume on. Okay. So this length I'll be considering 4 feet, or width I can consider 4 feet. Okay. Anyhow, one value is 4 feet. Other value is 1 feet only. Area I will be getting 4 feet into 1 feet. I'll be getting that in 4 square feet. H2, you can see from the middle of this one to the top side, how much you are getting that one. How much? That is 4 feet only. You can take that as 4 feet. Correct. When you are calculating, you can see the height, how they are taking it. When we are taking the height from the middle of the opening to the bottom, like that, you have to select it. Okay. Okay. And also, you have to find the leakage now. The area we have calculated. H2 is also there. Now we have to find the leakage rate. Leakage rate you can find from this table. From this table, you can see the term foot height of atmosphere above center of opening. Okay, what was this? Is foot height of atmosphere above center of opening. Foot height from the center of opening to above. This is a height. How much it is? 4 feet only. That you are having in the x-axis. Okay. Leakage rate, pound of carbon dioxide per minute. Through the opening, each minute, how much quantity of carbon dioxide can leak through one square feet. That's the rate. Leakage rate per minute you can find from there. And this one, 10%, 20%, 30%, this is your carbon dioxide percentage only. Okay, now, in our case, the carbon dioxide design concentration is 37. This foot height is 4 feet. Let's say that will vary with respect to the drawing. In our case, that is 4 feet. Now that is 1 feet, 2 feet, 3 feet, 4 feet. You can make a straight line in the top side. And our design concentration is 37%. This is 30%. This is 30% and this is 40%. 35% somewhere there, 37% somewhere here. So from this point, you can find in this, that will between, this is 10 pound of carbon dioxide, this is 20 pound. So middle you will be getting 15 pound, let's say 17 pound you can consider. 17 pound of carbon dioxide per minute per square feet you can see. Okay, 1 square feet. Let me select 17 pound, that is my leakage rate. 17 pound I have taken. Duration. This one is for per minute only. How much duration has to be considered? Correct. Leakage rate I have considered through that opening, each minute this much. But when we are designing, how much minute has to be considered? We can find below an opening that cannot be closed. Opening that cannot be closed, design concentration when you have to consider anticipated loss at the design concentration during 1 minute period only. For surface fire only I am calculating, you have to consider only 1 minute. 1 minute. So that's why duration I'll be considering 1 minute only. But if you are having 2 minute duration, accordingly you can do. Okay. Then how much value you will be getting? Carbon dioxide loss due to the opening, A1, area. Area is how much? 4 into 1, 4 feet square, multiplied by QL, leakage rate, how much? 17. Okay. Into 0.5. I will explain why this is 0.5 we are taking. 0.5 into duration. Duration, that is 1 minute only. 1 minute. If it is 2 minutes, you can take 2 minutes. Okay. Why we are taking this 0.5? Because half the value only we are taking. Leakage, we are multiplying with a half. Because you know, if you are having an opening, through half the opening, the carbon dioxide will be coming outside. Half the opening, the air might be going inside. That's why the entire volume through the entire area, the carbon dioxide is not going to come outside. So that's a concept they are suggesting. You want to consider only the half. If there is an opening in the wall only, the area of the wall opening can be divided by 2. 2 means you have divided by 2 or multiplied by 0.5 for the calculation, because it is presumed that the fresh air can enter through one half of the opening and that protective gas will exit through the other half. That's why this one we are multiplying with the 0.5. Okay. So by that calculation, how much you will get? 4 feet square plus 17 plus 0.5 plus 1. You'll be getting 34 pound. 34 pound you will get when you are doing this calculation. Okay. How much it is? 4 feet square. Okay. Multiplied by leakage rate, multiplied by 0.5 into the duration. You'll be getting 34. So along with this 102, you have to add 34. So 102 plus 134, you'll be getting 136. That is our value Q3. Q3. The next one, unstoppable ventilation.